Hello, everyone. I'm very glad to be here to share our recent work at annual technical conference. I'm Weihao from Shanghai Jiao University. My supervisor is Professor Chen. The title of our work is DVABatch, Diversity-Aware Multi-Entry Multi-Exit Batching for Efficient Processing of DN Services on GPUs. It is about efficient processing of batched DN queries on GPUs. I will start from background and motivation. Nowadays, DN techniques are powering cloud services, for example, image classification and speech recognition. Since user queries have stringent QoS requirements, dedicated accelerators like GPUs, TPUs, and NPUs are used to speed up the DN inferences. GPUs have much computing power. Therefore, it is important to process DN-based services efficiently on GPUs. A common practice is using batching to improve computing efficiency. Here we show a simple example of batched image classification. We first deploy the models on GPUs by serving frameworks like Triton, TensorFlow Serving, and others. Then the frameworks provides a batch entry to batch the accepted queries. Commonly, they also provide a time window to batch the queries, as queries often arrive randomly. After that, the batched queries are processed at once with high parallelism on GPUs. At last, they will exit the batch together and the results are returned. In this case, we improve the utilization of GPUs and guarantee that the queries are processed as soon as possible. However, our observation reveals that diversities diminish the efficiency of such single-entry, single-exit batch scheme. We will introduce 3 diversities in this work, and there are more diversities in production. First diversity is the input diversity. Input diversity widely exists in DN services, for example, natural language processing services. Here we show the sequence length distribution in 10 workloads of the GLUE dataset. Most sentences have 5 to 20 words, but some have more than 100 words. For these models, the input of short queries is padded to the same size of the longest. In this case, they can be batched to run. The benefit of batching may be negated by the wasted computation for the padded part. An ideal batching strategy is shown in the right. The batch is divided into 2 smaller batches, one for short queries and one for the long queries. Second is the operator diversity. The DN operators require different batch sizes to fully utilize the GPU. As shown in the figure, for GEM-A operator, batching only increases its latency without improving the processing throughput. For GEM-B operator, using a batch size smaller than 8 is not able to fully utilize the GPU. The processing time does not increase until the batch size is larger than 8. The preferred batch sizes of GEM-A and GEM-B are 1 and 8 respectively. While all the operators of a DN model share the same batch size during inference, in single entry and single exit batch, they have different preferred batch size. Here we show a simple example. We assume operator A prefers batch size 4, operator B, C, and D prefer batch size 1. The batch of operator B, C, and D result in longer latency without throughput improvement. An ideal batching strategy is that we can run operator A with batch size 4, and we split the batch into 4 smaller batches with batch size 1 at operator B, and then we run the small batches sequentially. In this case, the latency is reduced. The last one is low diversity. Service queries do not arrive in a uniform interval. In this case, the number of queries collected in a single batch time window varies. As shown in the figure, when a load bursts, the subsequent queries have to wait for the completion of a previous non-full batch. This results in the long latency while there is still hardware resource idle. Ideally, if we interrupt the ongoing batch and merge them with the newly arrived queries, we can make better use of the GPU hardware. In summary, single entry, single exit schemes show weak support for serving diversity. Firstly, it assumes that batch always have positive effects for improving hardware utilization. Secondly, an ongoing batch made by inappropriate decision cannot be interrupted for adjustment. Thirdly, the single entry, single exit scheme cannot be configured for support various diversities. We now may have an idea. Can we have a multi-entry, multi-exit batch scheme for addressing these concerns? This is what exactly DVABatch brings in. Now we introduce the methodology of DVABatch. DVABatch is a runtime batch scheduling system. It can be integrated into existing DN serving frameworks. It supports multi-entry, multi-exit scheme for adjusting the batch on the fly. The proposed holistic solution can also be configured for different serving diversities. To support the multi-entry, multi-exit scheme, we first slice the model into multiple stages. Each stage is executed by an executor. The executors are connected by batch queues. These executors and batch queues are coordinated through a batch table. The batch table supports 3 meta operations: new, stretch, and split, to meet the requirements of multi-entry and multi-exit scheme. For a new DN service, we identify the serving diversities through input check and kernel profiling. Then we will slice the models. After that, we load the models and customize the scheduler accordingly. Finally, DVABatch is ready to exploit meta operations for efficient processing. As mentioned, the key abstraction of DVABatch is the meta operations for adjusting ongoing batch. They are implemented by coordination of batch table, stage executors, and batch queues. Detailedly, the new operation will add a new item in batch table for the accepted queries. The stretch operation will merge new accepted queries with an existing item in batch table. The split operation will split an existing item in the batch table into several items. New batches will be pushed into batch queue through these meta operations, and the executors will process the queries and update the batch status accordingly. Executors are processing queries independently. The left figure shows the way the stages are connected. Multiple buffers are used because multiple batches may be active concurrently. An executor needs to obtain an input-output buffer pair before it can process a batch. Therefore, we need to manage the stage executors. Firstly, we need to avoid hazard during processing queries with multiple buffer pairs. To achieve this, we set 4 states of buffer pairs used for connecting adjacent executors and 3 states for a stage executor. The right figure shows the state transition rules. A stage executor can process a batch only when it successfully obtains a legitimate buffer pair. And a buffer pair is legitimate when both the input and output buffer are available, or the input buffer is available but the output buffer is invalid. However, these state transition rules assume all the stage executors use the buffer pairs in some fixed order, for example, ID order. It only works well for the single entry, single exit scheme. These rules will encounter the validity problem for the multi-entry, multi-exit scheme. In multi-entry, multi-exit scheme, stretch and split will merge or split output into multiple buffer pairs. That means some stage executors may use more buffer pairs than others, and the access order of these buffer pairs is scrambled. As shown in the left figure, when executor I is using BP3 for execution, executor I plus 1 is active with BP2. Such inconsistency invalidates the above stage transition rule. The stage executors need to run multiple batches in parallel for load diversity and input diversity, but run batches sequentially for operator diversity. As shown in the right figure, the stage executors always run in parallel even if only one buffer pair is used. Because executor I legitimizes BP1 for executor I minus 1 after it completes the execution. Executor I minus 1 is active with BP1 when executor I plus 1 is in working states with BP1. In this case, executor I minus 1 is able to run in parallel with executor I with plus 1. To address above two problems, we add an extra state for executor and moves the time point for legitimize the used buffer pair. First, the check-in state guarantees the correct access order of buffer pairs, and we only legitimize the used buffer pair after executor enters active states. This will enable a serial work manner where only one buffer pair is enabled for all executors. Now we present the interface of DVABatch to create policies. Each stage executor runs in a while loop to execute the batches. The stage executor calls schedule to schedule the batches. Inside the schedule function, the stage executor updates the batch table and performs meta operations if user-defined conditions are satisfied. In this way, users can define conditions to adjust the ongoing batch. With the three meta operations, we can create policies for the involved diversities. For input diversity, we split the accepted queries into small batches with similar sequence length and run them in parallel. For operator diversity, we split the accepted batch at a specific stage and run them in serial. For load diversity, we stretch the insufficient batch with newly arrived queries. These policies can coexist in a single DN service. Now we will present the evaluation of DVABatch. We use 6 models for evaluation: breadth-based, breadth-large, with input and load diversity, UNet, LinkNet with operator diversity and load diversity, VGG and ResNet only with load diversity. For simulating input diversity, we use glow dataset to generate input data. To simulate load diversity, we generate load with Poisson distribution. We compare DVABatch with 2 baselines, zero batch and delay batch. Zero batch batches queries without time window. DVABatch batch queries with a hand-tuned time window for high throughput. Compared with ZeroBatch and DVABatch, DVABatch achieves better average latency performance on the high, medium, and low load. To show the robustness of DVABatch, we also evaluate DVABatch with a stepping load. The stepping load increases load gradually. All the benchmarks have lower latency with DVABatch in all cases. For bird base and bird large, DVABatch also increases peak throughput due to removing computation for padding. To conclude, DVABatch makes following contributions. We propose a multi-entry, multi-exit batching schemes for efficient DN service processing on GPUs. We provide a general scheduling mechanism that leverages the meta-operations and state transition diagram to create policies for different serving diversities. We reduce 46% average latency and achieve up to 2.12 times throughput improvement for the involved serving diversities. DVABatch also brings some implications for future DN servings. First is omnipresent diversity. Existing DNs may have a dynamic architecture in depth, width, and routing. As more dynamic attributes emerge, diversity spreads across new DNs. DVABatch is flexible to tackle many diversities among them. For example, layer skip early exiting models require to split batches into smaller ones. Second, intramodal scheduling. As DNs grow larger and show more diversity, the execution of DNs cannot be treated as a single function call. Intramodal scheduling is a trend for DN inferences of large models. That's all, thanks. Any questions?